Okay, Raju, then we will start the session. Now, whereas for this purpose, I am not creating a geometry. We will start with an existing geometry.
Okay.
Okay, we will start with an existing geometry, and we will make the settings accordingly. Okay.
Okay.
Now, let's. What I will do is I will use paraview. I have a existing geometry pipe.stl with all the patches named separately. If I open that in paraview, you will be able to see so many what is that so basically this is like an exhaust manifold. Okay, and you have so many inlets and one outlet.
Okay.
Yeah. So exhaust manifold, basically it is collecting from the different exhaust of the engine, and then you have one outlet with it. Now, I really do not know the dimension of it, of all these things, but yeah, let's do some sort of a trial and error method to see
Okay.
how the dimension is looking like. Okay, and yeah, first step is we will load the OpenFOAM environment OF2412 and go to something called as foam tutorials, where for basically how we are going to create a case is, right, we will take an existing case setup and copy it to our thing and replace the files and settings on the boundary condition based on our geometry. Okay,
Okay.
basically
Okay.
for first simulation we are going to do a simple incompressible turbulent flow case, pipe flow case kind of thing.
Okay.
So here, if you have to first go to, you have to load the environment and go to foam tutorials, and inside foam tutorials, inside the tutorial folder, go to the incompressible folder, and steady state incompressible flow turbulent flow simulation, it is mostly with the simple foam solver. Go to the simple foam solver, and then there will be a simple case called pitch daily. Okay,
It's really
pitch
okay.
daily. Okay, we will go into the directory. I will just note down the path of that directory. Basically,
Okay.
my idea is that copy this, and wherever we are going to run the simulation, that folder we will copy that pitch daily. Okay,
Okay.
maybe this is the case setup, so we will create two folders. One is the case and other is the mesh. Okay, first is this pitch daily. I'll rename it as case. Okay, and the same pitch daily, the same case, I will copy the mesh where we will be creating the mesh. So we
Okay,
will,
same case, like the same folder, entire
yeah,
folder of Peach Daily,
yeah,
you renamed as some case, and then again you copied it and as mesh
yeah,
folder,
yeah,
means
yeah,
same.
yeah. So I will come to that. So basically, my idea is that, so for meshing, a lot of things are not needed, but just in case it is since it is very similar, I mean the base cases which are needed to do the base files that are needed to do the mesh, that will be already in the case folder. That's why I copied it there. Now mesh we are going, and we don't need to have boundary conditions and all, so I'm removing 0. This constant folder also is not needed. Basically mesh requires only the system folder. Okay, and the system folder also, a lot of things are not needed. So for example, only you need 3 files: control dict, fv schemes, fv solution. So yeah, the thing is, uh, block mesh and streamline, those things are not needed. Only the 3 things are needed: control dict, fe scheme, fe solution.
Mhm.
So here I am coming, these functions are also not needed. Very simple control dict is needed. Control dict is like it just to say that it is a open form directory. It is of nothing. It is of not much use at all. So
Mhm.
a very bare minimum control dict is required. That is more or less sufficient to do the meshing part. Okay.
Mhm.
Now the geometry, it will always go into a folder called as constant trisurface. Okay. I will create constant folder, and inside that constant folder I will create a trisurface folder. Okay. Now I will copy that pipe thing, that is the entire geometry, into this constant trisurface. All is clear with that until now?
Yeah. So this is always standard names, this constant tri-surface, or
Yeah,
it
yeah,
is
yeah.
like.
Constant trisurface is where, so for example, to make the mesh in snappyHexMesh,
Mhm.
it is always better to put the STL file which you want to mesh it in the constant trisurface folder.
Okay. And we have now constant folder and system folder. And in system folder, we have only three things now:
Yeah,
control dict, FE schemes, and FE
yeah,
solution.
yeah.
Okay.
Okay.
Yeah.
Now, first step is what we will do, Raj. We will do something called as surface check.
Mhm.
Before that, we have to load the OpenFOAM environment, do surface check, and put help. Okay.
Mhm.
The surface check main idea of the surface check is it to verify that our surface is watertight or it has issues or something. For example, in snappyHexMesh, even though the surface is not closed or something, it will still create a mesh. The leak closure will be done automatically. But
Mhm.
in any case, it is better to create a closed surface so that we have a very good control over the meshing and the boundary conditions. Okay.
Mhm.
So the surface check command, if you look into help, you will know. But the standard format is surface check output threshold. I have to set it to 0, and the surface to check is the pipe.stl in constant try surface. So basically, what this output threshold does is, for example, let's say if you just run surface check on the file pipe.stl, it will create a lot of output files based on the amount of errors in your surface file.
Mhm.
So let's say your geometry is not watertight or something like that. It will write some phases where it is non-manifold, the leak is there, something like that.
Mhm.
I always use output threshold 0 because it makes sure that no extra files are written. It just checks the file and reports an output. Okay.
Okay.
So surface check output threshold 0 constant try surface. Now if I do that, and in OpenFOAM what I always do is I will run the command and save the output to a log file. For example, this is surface check, right? Log dot
Yeah.
surface check, so that
Okay.
we have some thing tail left log dot surface check. Okay, so log dot surface check, if you open it, you can see that there are so many inlet files.
Yeah, four inlets, one outlet and wall. Okay.
Okay.
So now, how if everything is not okay, then there will be some message which will be given here,
Yeah, yeah,
right?
yeah. So this surface
Mhm.
has no illegal triangles, right? If it has illegal
Mhm.
triangles, it will show that. It will
Mhm.
show that number of unconnected parts is one. If it is like multiple normals are there, those things will be shown here. Connected area with consistent normal. That will be like
Mhm.
if you have multiple orientations, multiple
Mhm.
surfaces pointing in different normals.
Mhm.
It will show the normal orientation to be inconsistent. Show 3, 4, something like that. Number of unconnected parts also it will increase. Those things.
Means like on some surfaces, like they're inconsistent normal. Suppose some wall is normal outwards and some wall is normal inwards, then it will show here
Yeah,
number of
yeah, yeah,
zones.
yeah, yeah. Okay.
Mhm.
Yeah. So this is done. Now we have to generate a we have to generate a background mesh for the geometry. Background mesh in the sense that OpenFOAM, you know, right?
Mm-hmm. Yeah, the cuts and
1 minute, Vedant.
the
Yeah. So background mesh in the sense, whereas snappyHexMesh, you know the procedure, right? The surface, entire surface, it will be enclosed with the background mesh, and then that background mesh will be used to make the mesh inside the surface.
Mhm.
You remember this step?
Yeah, I mean, like there is background mesh and entire surface is there, and wherever that surface will cut the background mesh,
Yeah, yeah.
there it will be the
Yeah,
snapping
yeah, yeah.
thing. Mm.
So basically, I have a Python script already, Viraj. So to do like let's say do these procedures, because these are like very repetitive procedures.
Uh-huh.
I will just generate the background mesh. First is we will look into the surface dot check to just see what is the bounding box. Bounding
Mhm.
box in the sense that it is -1 to it
0.03.
yeah, point 0 and things like
Mm.
that, right? So
Mm.
let's try to play around with the background mesh, because I don't know the dimensions of the geometry.
Mm.
Ideally we should know the dimensions of the geometry, but we will it doesn't matter. Generate background mesh, and if you run the help command, this is my script. This is not OpenFOAM's offering. This is my script.
Oh. Mm.
Basically, what it does is this generate background mesh. We have to give the path of the STL file, that is
Mhm.
constant tri-surface pipe, and then we have to give dx, dy, dz. Okay. Now what I will
Mhm.
do is dx, I will give 0.01.
This is the background mesh size,
Yeah, I mean the base grid size.
base grid size. Yeah.
Okay. Now the thing is we have to look the STL file and also the background mesh. Okay. So
Mhm.
to load a OpenFOAM case, a .foam file should be there. So what I will create is I will create a touch paraview.foam. It need not be paraview. It can be a.foam or any name.
Mhm.
There should be a .foam case. So paraview can pick it up that this is the OpenFOAM case and can open the mesh. What I will do is I will go into the mesh folder, paraview. Uh, I will open the paraview.foam, and if you look at it, this is how the background mesh is looking. Now let's also load the STL file.
Mhm.
The thing is, we
Wait,
have to have some
wait.
level of opacity to view what is inside, right?
Mhm.
Oh, okay. Not the pipe. I want the paraview thing. So basically, it is something like this.
Mhm.
Okay. Now this gives an idea, Viraj. So basically, if you look at this thing, the diameter, it is like resolved by how many cells?
Mhm.
1, 2, 3, 4,
7,
5,
8.
6. So we need at least one. I mean at least 7 into 2, 15 or something like that. Let's start with 15. When we are making the snappy mesh, I'm saying. So basically,
Mhm.
this level of refinement is not sufficient to for resolving the diameter of the pipe, because it will be very coarse.
Mhm.
You're getting my point, right?
Yeah, yeah.
So background mesh can be this, what we can do is we can improve the refinement levels while making the snappy geometry. That is the idea.
Okay.
Basically,
Okay.
this base grid size is level 0, that you have to keep in mind. And in
Mm.
snappy, we will be giving what are the different levels. I mean, for each surface, what is the level that we want, we will be giving it in snappy. So at that time you have to make sure that we will give a larger I mean more refinement while making the snappy mesh. That is the idea, Viraj. Okay.
Okay. But now when you did that your this Python script which is there, or some script which you wrote,
Yeah.
that generated this thing, yeah, and then you renamed it to paraview.foam, or
No, 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 no,
you
no.
cre-
So paraview.foam is like basically generate background mesh. It will create files in the constant folder. Basically, okay, I will show you what
yeah.
generate background mesh did. This generate background mesh, I have outputted those things in the program outputs folder. If you
Mm.
see, it will be running so basically I give dx dy 0, right? So it says
Yeah.
so many cells are formed and those things. And that
Mm-hmm.
mesh will be available in constant polymesh folder. Always OpenFOAM's mesh will be available in constant polymesh folder.
Okay.
So you look at a boundary, you can see the number of faces and other things. Also you can look
Mm.
at faces, owner, neighbor, those sort of things. It will be available in the constant polymesh folder.
Yeah.
The paraview.foam is dot foam, basically not paraview, any name, a dot foam,
Anything
viraj dot
dot
foam,
com.
anything, and
Okay.
dot foam should be there. That
Yeah.
dot foam folder, what it says is it says that it is a OpenFOAM directory, and read the
Mm.
mesh and the information and the results from it. That's the thing. For
Okay.
paraview to read it, it is a dummy file. It
Mm-hmm.
doesn't have any meaning.
Okay.
Okay.
But that is that dot form file which we folder we have created, that is in our main folder, right,
Yeah,
where
yeah,
we
yeah.
are doing this.
Mesh folder. Yeah.
Mm. Okay.
Okay, right?
So this script we will have to have, right? Otherwise, like the procedure will be something else, right?
Otherwise, it will be like you have to manually do it. It will become complicated.
Okay. Okay. Mm.
So basically, the script will create a
Mm.
block mesh dict. The thing is, these
Mm.
things you have to write it out.
Okay.
It becomes complex, right? Like you have to know
Okay.
the
Okay.
bounding box, what is
Mm-hmm.
the base grid size, those sort of things. Yeah.
Okay.
Okay, Raj, shall I proceed?
Yeah. 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 Yeah.
Now, since we have generated the background mesh, now it is time to generate the snappy mesh. So, I'll just clear it, go from the start. Basically, that command is generate snappyHexMesh dict. Okay,
Mm-hmm. Okay.
just run it, and it will ask for some inputs. We have to go through it carefully. Geometry input, geometric files in constant tri-surface folder, only one. And you have to select what. So basically, why I have given it is sometimes you can have multiple STL files. So
Mm-hmm. Yeah.
to just select them. Now it is just one. So just click, press that one and enter. And do you have any edge meshes? No, we don't have any edge meshes. So just press enter.
Mm-hmm.
Enter the number of additional standard shapes for volume refinement or separate cell zones. I mean, for the moment we don't need it. These are all advanced settings. For the
Mm-hmm.
moment we don't need it. For example, MRF simulation, we need a cylindrical thing around the fan and all, right? For
Yeah.
those things. But for now we don't need it. Just put 0 and enter. Okay. Now
Mm-hmm.
refinement settings for feature edges, volume refinement you're doing. Volume regions are pipe. Select volume regions with specific refinement levels. So this volume region, we want to refine it or not? Yes, we want to refine it because the base grid size is very coarse. We want at least one level finer. Okay.
Mm-hmm.
So what I will do is, yes, I will select this number, and then what is the volume refinement inside the pipe? Base grid size is 0, so volume refinement level is like one level higher than that. One level higher than 0 is 1.
Mm-hmm.
Okay, and resolve small gaps with finer refinement in the pipe level or not. For example, some cases, let's say MRF cases or any blade tip, the clearance may be very very small. So
Okay.
everywhere we need not have very fine meshes to resolve that. Only when it detects very small gaps, we want the refinement level to increase. Okay, in those scenarios.
Okay.
But here it's a very simple geometry. We don't have such things. So I'll just put n and enter. Okay. Now enter the global surface refinement levels of the pipe. Basically, what is the thing is surface refinement is this. You will specify refinement levels for individual patches. For example, the wall, the inlet, all the inlets, the outlet, those things. This global refinement is like for the entire geometry for on the surface. So what I will say is I want the surface to be one level more than the block mesh. So minimum is 1, maximum is also 1. I am giving 1. Enter local refinement level for the boundary inlet 1. This also I will give 1. What is the type of the boundary? So inlet is not a wall, it is not a phase zone. Phase zone is for MRF zones, so it is of type patch. Similarly,
What?
this
What?
also
Sorry.
1
Sorry.
1.
Sorry. Mm. Okay.
It is of type patch. 1 type patch. 1 type patch. And outlet also 1 it is of type patch. Now the wall is of wall also I want 1 of refinement level. It is of type wall.
Mm.
Okay.
So now global surface refinement level is one, and everything else also is one. That means, like all surfaces will be refined by one level.
Yeah, one
Then
level higher.
there is.
So why I am
Mm.
giving this is that these settings are
Mm.
I mean this refinement level and all we have to I mean based on the geometry only. First we have to start with a very coarse setting which is
Yeah.
reasonable, and once we have to go and look at the mesh, and if the patches are not resolved correctly or the edges are not captured, that specific
Mhm.
location we have to change the refinement.
Okay, so what I'm saying is that if it is going to ask us every boundary, what we have to give the refinement level
Yeah.
for every boundary, then why it is asking for the global refinement level
So
also?
global in the sense that sometimes the patch it will be in the geometry, but you won't be giving it here.
Uh-huh.
So the patch will be in the geometry, but you won't say whether it is a wall or something like that. Then OpenFOAM needs
Okay.
some sort of an idea.
Okay.
Even here, what you can do is you can just when you look at snappyHexMesh, you can you can know that
Mm.
inlet 1, inlet 2, these things you need not give. It will automatically create those patches.
Mhm.
But the refinement levels it will take from the global value.
Okay.
My script is asking all the questions, Viraj, but it won't be the case
Okay.
when you are making the snappy thing. Yeah.
So this is okay. This is your script which is asking all these
Yeah,
things.
yeah.
Okay.
And this one, enter the number of cells between mesh levels. So basically, what is the case is, this is a cut cell Cartesian grid, right? Cartesian
Mm.
type of mesh. One cube
Mhm.
will be level 0. Let's say the next level will be like it will result in 8 cells. That
Mhm.
one cell, if you split it, it will be 8 cells, correct?
Mm.
Now, so basically, for example, on one surface you can have level 1, whereas interior of the geometry maybe you will have level 0.
0.
So that wall to not only wall, I'm saying any place you can have a very fine refinement level. From that fine refinement level to the next refinement level, or a small coarser refinement level, if it has to go, whether it wants to go faster or slower, in the sense that how many cells you should have in between, because
Mhm.
because the thing is in converge a larger cell can be connected with the next level, because converge allows hanging nodes,
Mhm.
right? OpenFOAM doesn't allow, snappyHexMesh doesn't do a hanging nodes, OpenFOAM also doesn't allow a hanging nodes. So you should have intermediate cells.
Mhm.
So between two levels, a coarse level and the next level of cell, that is the cubical cells, what is how many cells you want, how many transition cells you want, that is the thing. This is not to be confused with inflation layers, Viraj. This is just volume
Uh-huh.
itself, how it grows
Yeah.
from a finer cell to a coarser cell. Next level,
Mhm.
how it grows. I always
Okay.
go for option 2.
Option 2.
Yeah, yeah.
Hmm.
And one more thing is this XYZ at this point becomes very very important. So uh, we have to give a point which lies in the inside the pipe. Okay, otherwise
Okay.
it will become an issue. What I will do is I will
Mhm.
click this. Uh, yeah. Okay. Uh, gives an idea. So basically, Viraj, so we have to give an inside point, right? Like my idea would be click on the pipe, then
Mhm.
click this plot over line. We are not going to plot anything, but this is just to know the extents of the geometry. So it starts from somewhere here and it goes until here. Okay.
Mhm.
So this will be minus. It starts from minus 1.0583. Okay, and it
Mhm.
is minus 0.55, something like that. What we can do is filter search sphere. I will just create a sphere and I will where is that? Yeah, the sphere is so huge. I'll reduce the size. Okay, now ideally what you have to go, you have to move down the y-axis and the radius is still huge. I will give 0.05 theta, I will give 20 so that the sphere looks better. Okay, now Viraj, you get my idea. What I'm trying to do is I'm just trying to put this point in the pipe somehow by
Mhm.
adjusting the center of it.
Okay.
Let's see whether this works out. So if I give minus zero point 0.5, it has come here, and now the only thing I have to do is I have to go in the z direction, negative z direction, to go through the pipe. So I will give minus zero point 0.1. Okay, it is already in the pipe. Now let me reduce the radius of the
Yes.
sphere and also make this pipe little transparent. We have to just be
Uh-huh. Yeah.
100% sure that this point is inside the pipe, because what it do is if you give a point outside, it will be like a aerodynamic case.
Mhm.
It will remove the cells inside the pipe and
Uh-huh.
only keep the
Okay.
cells outside. If you put a points inside, then it will be an internal flow case.
Mm.
So you get my point, Viraj, that how I
Yeah,
am
yeah,
how I
yeah.
am finding the inside point is I'm just using pipe. I'm putting that line filter to get an idea of like what are the extents of the thing, and then I'm just creating a sphere filter and trying to
Mhm.
put that ball inside the pipe. Now
Mm.
I have the center, that is the inside point, minus 1, minus zero point 0.5, minus zero point 0.1. So this is the value I have to give: minus 1, minus zero point 0.5, minus zero point 0.1. Okay.
Yeah.
uh, Type of snapping feature edges. This is basically the thing is a lot of sharp edges are there, right, at inlet and outlet or corners and all. You can you can snap those edges or put refinement on those edges explicitly or implicitly. Explicitly in the sense that you have to give a separate edge mesh. uh,
Mhm.
STL is a surface mesh. You have to give an edge mesh, and Snappy will look into the edge mesh wherever it is located, and basically there it will refine or capture those edges. But let's say you
Another.
don't have those edges. We don't have those edges at the moment. We only have the STL file. We will go with the implicit option. Implicit option works most of the time.
Means you have to give some angle or something there,
No,
right?
no, no. Yeah, feature angle it will automatically take. We need not worry about it. 30 degree.
Okay.
Yeah, 0. And do you want to add boundary layers? We will say yes. Where you want to add boundary layers, I just want to add it on the pipe wall.
Mm.
So inlet, I, these things I will give no.
Yeah.
Pipe wall I will give yes. Okay,
Okay.
number of boundary layers, let's say 3.
Mhm.
Okay. Now that snappy hex mesh dict is written, Viraj. We can look at it. So, but you need not go into detail of it. Whatever information that we wrote, those things
Yes.
would have appeared here. The boundary conditions and all sorts of things are written. Okay, already. Okay.
Uh,
Now, the only thing is left is we have to run the snappy hex mesh. Snappy hex mesh. I will always go and save it to a log dot snappy hex mesh so that we can use it later. Tail f log dot snappy hex mesh. So the mesh is being made. Yeah. Let's look at the mesh, Viraj. Now go to paraview. We can delete these things because even the pipe is not needed anymore. And since our mesh has already been created, the mesh will be created in multiple folders 1, 2, 3. So we have to load those time, right? So what you have to do is you have to click this and you have to reload files.
what time you are mentioning? Like you said, it is created in times, different times.
Yeah, yeah, yeah. So basically, I will reduce the opacity. Yeah, this. So you had the background mesh, Viraj. Now the background mesh is gone, and this is the castellated thing,
Mm-hmm.
but it is not still snapped to the surface. Okay.
Mm-hmm.
Now, if you look at it, next thing, it would have castellated nicely.
Yeah.
Okay, so it has sit on the surface. For most of the simulation, Converge also works with this type of mesh only. For most
Mm-hmm.
simulations, this is good enough. This mesh is good enough. Like except
Mm-hmm.
aerodynamics or very specific cases where you want the heat flux to be captured accurately, cavitation captured accurately, and all, then you need the boundary layers, right?
Mm-hmm.
Otherwise, this mesh itself will be decent enough. Now we have also created the boundary layer. Boundary layer will be in the third. You can see that boundary layer also is generated.
Wow, nice.
Yeah. So
Yeah. What?
here it has not generated, but we have to see the cut section. And also our mesh is also not very good, I would say, because it's still 15 cells across diameter. That is not good. Typically we give at least 20 cells, right? So I want z normal. Let's say z normal, but I want it to go inside. Yeah, here show plane is cut off, wrinkle slice. Yeah, I think boundary layer has generated. Only here it is failing, but it is fine. You see the thing, right?
Yeah.
So we have generated the mesh with snappyHexMesh.
Okay. So why it failed there? But because it is not some very complicated stuff there, right?
The thing is, what happens is if it wants to put mesh, it will result in poor cell quality there. If
Mm-hmm.
it wants to put boundary layer mesh at 90-degree angles, it will
Mm-hmm.
result in poor cell quality, and that's why sometimes it just avoids it.
Okay.
And it is mostly irrelevant where there. I
Oh,
mean, closer to the outlet.
okay.
Yeah. So, whereas I think today,
Mm-hmm.
I mean, we have took the geometry, we have created, like, I have gone through the procedure of creating the mesh. Okay,
Mesh.
then tomorrow maybe we can do just use this geometry, set up a case, run it, and see the results.
Results.
Okay,
Yeah.
I think I will